Welcome to this webinar by Oxford Technical Solutions. In this webinar, we will describe the motives of why you would want to operate a survey-grade inertial navigation system on your unmanned aerial vehicle. Within all types of flight operations, it is important to understand the dynamics of how your aircraft is moving. What direction is it flying in? Is the aircraft rolling, pitching, or yawing? Is it accelerating or decelerating? A system that we can use to measure and record these dynamics is an inertial navigation system, otherwise known as an INS, where an INS is a computer system that takes input from a global navigation satellite system, such as GPS, and an inertial measurement unit, otherwise known as an IMU, which measures the orientation of the aircraft. While understanding the flight dynamics is of course important for piloting the aircraft, when undertaking aerial survey operations, it is particularly critical to understand the geometry and relationships between the aerial platform, its imaging or mapping sensor, such as a camera or LiDAR system, and the ground below. This is the first reason why the grade and characteristics of the onboard INS are vital to survey applications, as even the smallest deviation in movement of the aerial platform will affect the relative position on the ground that is being imaged by the mapping sensor. Before INS systems were available, a process of aerial triangulation was employed in aerial mapping operations. This involves placing and surveying a collection of benchmarks on the ground, known as ground control points, across the area that is to be mapped. And this is all done prior to flying the aerial mapping platform. These ground control points will be marked with targets that will be seen in the aerial platform flying overhead. Once a flight is performed, the mapping technician will identify the ground control points in the images taken by the mapping sensor. This will assign the corresponding pixel in the image with the known X, Y, and Z coordinate of the corresponding ground control point. Following this, through a process known as aerial triangulation, coordinates of pixels in the rest of the images are interpolated relative to the known positions across the image. Within the relatively new UAV aerial survey and mapping industry, aerial triangulation is still a process commonly undertaken. Compared to manned aerial mapping operations, the size of the areas surveyed by UAVs are still relatively small. Also, to minimize the weight on the UAV, consumer-grade cameras are frequently used. While aerial triangulation can be relatively low cost in terms of the equipment required to undertake them, there can be significant costs incurred when performing wider area mapping or when mapping in inaccessible areas. The accuracy of the resultant georeferenced image will be dependent on the volume and density of ground control points surveyed, which leads to increased field time during the operations. There may also be health and safety implications when sending ground surveyors to a site, which could of course also be the reason why aerial UAV mapping applications might have been deployed in the first place. In manned aerial survey operations that might be operating on a regional or national base scale, it has long been recognised that utilising an INS will increase the efficiency of a survey and reduce the requirement for a high density of ground control points. Through using an INS to record the location and dynamics of the aerial platform, the exterior geometry of the onboard mapping sensor can be calculated. In layman's terms, the INS is able to record where the sensor is pointing. By applying this model of external geometry to the data collected by the mapping sensor, it is possible to directly assign known coordinates to the data collected. In the case of aerial imaging, these coordinates might be applied to each frame of an overlapping image set. Or if collecting LiDAR detection and ranging data, otherwise known as LiDAR, this model permits individual coordinates to be assigned to each individual data point collected. This process is known as direct georeferencing. With the increased use of UAVs for mapping purposes, and with it the miniaturization and development of specialist sensors for mounting on these UAVs, the efficiencies brought by direct georeferencing workflows are also being recognised in the UAV community too. So given that a UAV's flight controller system might already include a GPS sensor and an IMU, one question that you might be asking is why a separate INS system is needed in the first place. Firstly, the flight controller system is designed to work in real time and usually within tolerances that are wider than those required for mapping purposes. This means that the grade of components does not necessarily need to be as high as those required on a mapping system. As UAVs can be used for a wide range of applications other than just collecting survey and mapping information, the overall design of the UAV, including its flight controller, is often designed to be fit for purpose for both safe flight operations and to fit within a competitive price point. To enable data to be collected in both an accurate and consistent manner, a survey-grade INS does not just rely upon data from a GPS or an IMU alone. GPS data is not perfect. It is dependent upon environmental conditions and the configuration of overhead satellite constellations. It also usually collects location data at a frequency that can be slower than the speed that the aircraft is moving. An IMU, on the other hand, will provide information on how the UAV is moving, but will not tell you where the aircraft is. Through analysing both the global navigation satellite system data and the IMU's orientation information, the INS records a trajectory file of the UAV's flight path. Through applying a range of statistical filters, the INS computes a best estimate of position based upon these inputs. In the case of a survey-grade INS system, this collection will be measured at least 100 Hz, and so in effect provides a continuous trail of the platform's position throughout its flight. It is then possible to further post-process and refine this trajectory. In this post-processing step, it is possible to assess whether the originally calculated estimate of position for a given data observation is correct, based upon the positions that have been calculated for observations both before and after it. The result could be an adjustment in the position of that data point, and if this operation is performed recursively, the other locations recorded during the flight. The result of using the INS therefore enables a UAV-based aerial photography mission to be undertaken over larger or more elongated areas using fewer ground control points, while on an active sensor such as the LiDAR system, the trajectory information collected by the INS is a necessity for any type of mapping operation. So now that we have described what an INS is and the principles behind direct georeferencing, let us remind ourselves why we would consider using a survey-grade inertial navigation system such as the OXTS XNAV 550. The fundamental reason why we would use an INS is to undertake direct georeferencing to reduce field costs, add automation to your mapping procedures, and be able to undertake UAV mapping operations over larger or increasingly inaccessible areas. By deploying an INS as part of an integrated mapping system that is to be mounted on a UAV platform, it means that a refined best estimate of position can be calculated for the platform that is better than what the UAV's own flight management systems can provide. All this means that the operator can be confident that survey-grade data can be still collected regardless of the type of UAV platform that the mapping system is mounted on. A direct georeferencing workflow can lead to reduced fieldwork time and the ability to map ever larger areas. Due to the overlap requirements of aerial photography when mapping linear features, such as transport networks and right-of-ways, direct georeferencing can enable mapping operations to be potentially carried out using fewer flight lines and fewer ground control points. Finally, given that it is now commonplace for UAVs to be used as a cost-effective means to collect data across dangerous or inaccessible areas, Direct georeferencing enables mapping operations to be undertaken in a manner that minimises risk to field survey personnel. Thank you for your attention during this webinar. Should you like to find out more about how the OXTS XNAV 550 can optimise your UAV mapping operations, please click on the link below.